All right, good morning and happy Sunday. It's October 1st. And I'm planning on doing a post-mortem analysis on my contest I did yesterday with y'all. So I got two, and then I got stuck on the third one. And I realized a pattern. Whenever I get stuck on like one of these first couple ones, it's like kind of tricky. Then I end up like not getting any of the other ones either. Usually it's like, okay, get a dip on the confidence up here and then often don't get these ones over here. But I was looking at Q3 and Q4 in some folks' solutions, and this one looks like it's just kind of like a tricky one. So that threw me off. In Q4, actually, I went to look at my thought process here during the contest, and I'm pretty sure Union Find does work. I don't know why I didn't implement it. I think, like I mentioned, I lost some self confidence on Q3, and then I didn't see what was right under my nose for Q4. So Q1 was something I solved in a minute and 26 seconds. So that's pretty decent. So basically read the problem statement and type it out real quick. So the question was the minimum operations to have all the values 1 through k inclusive. So basically I create a total t that will return for each iteration for which this loop is not satisfied, keeping track of a set of what we have, which are values less than or equal to k, which we need to have as 1 through k inclusive in order for this constraint to be met. So when this is false, the cardinality they set have, that's the length of what we have, is equal to k. And we exit and return the total t times this loop is executed, right? So each time we just check for the back, add it onto what we have, and pop off the back. Okay, so that's Q1. Q2. So this one I did way too difficult. I think there's a much more simple of one way of really consuming threes over twos. So I ran into this bug where I did a handful of twos instead of two threes and two twos, right? Or something like that. So I came up with the overly complicated solution. I think it's kind of cool though. Basically using dynamic programming to go to consume the twos and the threes and then accumulate the count here as our total at the end. So basically take the frequency of each character or integer value, the frequency of each integer value of the input array A, and then accumulate the sum, which would be the minimum operations to reach each total t, right? Which is accumulated in reverse. In the base case 0, it takes 0 operations to reach the sum of 0. And then going from, actually we can go from 1 to t plus 1, which would be 1 to t inclusive. We don't have to go to 0. There'd be a small optimization here. Okay, so anyhow, Q3 is tricky, but I'm pretty sure we can do Q4. So that's what I'm going to focus on here. It's 8:55 in the AM. Question, union sign, right? Union fine. Union fine seems like a legit approach. So why didn't I implement it? Yeah, so during the contest, I think during the contest, I got about Q3, which was tricky. I think, yeah, it's tricky. Okay, so anyhow, it is 8:55 in the AM, and I'm gonna jam on this thing here. Okay, so call this thing N, this thing E, and then this is, we want to call this thing cost or something, maybe something smaller, just A, how about, and then T will be our target. Okay, so we'll do union fine. Yeah, so the game plan will be go do DFS bottom up, accumulate total values of each node. When the total is evenly divisible by t, then +1 for the component, right? Number of connected components. And zero out the total as the recursive stacking lines for that use case. Yeah, so in this case, we don't even need to use union find, right? If we just use DFS, right? So this is the game plan. Okay, 8:55. It took about 2 minutes for the game plan. It's 8:57. Let's should tack to where we are, right? I'm not using all my time. It'd be cool to be a contestant rather than a participant, right? Okay, so anyhow, let's just do this stuff. Go. So we have two things to pop up. One is the total as we go, which will be accumulated. And then the other thing is the number of connected components. So let's let the number of connected components, just T, right? It's fine. Non-local T is what we'll update. This is our node. Actually, how are we going to track this thing? We want an adjacency list of parent to child nodes. Then we want to go from the root. The root's not always guaranteed to be zero, though. If it matters how we traverse the graph, even. Traverse the graph. Yeah, I guess it probably doesn't matter how we traverse the graph, does it? This could be the root as well. And as long as we accumulate the total bottom up, I don't think it matters. Okay. Just start at any old node then. We do need an adjacency list though, right? So I'm gonna actually traverse this thing. Default, default dictionary set. So each edge UV in the list of edges. U is adjacent to V and the V is adjacent to U. Just call this thing U. Turn T. Go 0 through n-1, right? Okay, so we'll just start at 0. Right, that shouldn't matter. Actually, I wonder if that does matter. You know, just assume it doesn't, and we'll fail forward if it does. Does this matter? Where we start? I don't think go everywhere, right? Should be okay. Okay. Actually, instead of T, let's do this guy fast. How about start fast as we're trying to maximize. T is 0. Be the actually let's do this A sub the index U for V in adjacent to U. See, hold on, if T. So recursive stack on ones to propagate the total. If T modulus T and it's evenly divisible by that. Zero this thing out. Increment best. T plus equals go V. Let's call this thing just copy and paste that for now. That's okay. We're showing T at the interior. So total is propagated as a recursive stack on wines. Greatly consume it here if we can. Wait, does that work? I think it does. Okay. Let's see what happens. Let's just run this thing. Oops, I need to check track of what we've been seeing. Set scene. If you and scene return 0. Oops, I need to add it to scene. Scene oops, add view. 0. Uh-oh. Okay, so we're starting at 0. Going, there's our total. To view. Let's do this, do some printf debugging. Okay, it's 904. 904. Debugging. You scene total. Tab this over. Okay, let's see what total we get. What's going on here? Oh, oops. Let me empty set first. The recursion is going nowhere. Oh, scene. Oh, okay, yeah. Let's see. Scene. Okay, that looks good. Okay, 2 and 2. All right, and then 3 should be the output for this guy. Oh, getting 4. too many for this guy. T and this guy. Let's see what's going on here. Focus on the second one. Screenshot this real quick. Debug what's going on. Okay. We start from 0. You don't want to keep track of this too. Hold on. Keep all this stuff in the same window. All right, there's our mapping between the nodes and their values. Okay. So let's see what's going on here. We start at 0, which has the total of 3. Okay. Get a 1. Down here to 1. 0. Let's see. Actually, let's print out when we increment fast. Okay, 1. Best 2. No, I don't have to add 1. So it'll be okay 2. Okay. Oops. Let's see. All right. Go back to these guys here. Okay, see what's going on. Okay. Go from 0. Total is 3. Add on the total. Okay, so we call it 3 itself. That looks good. Then we go to 1. No 0. From 1 we go aren't we going to when we go to 3, total is 1. I get a 4. The total is 5. What's the total of 5? Let's already go to 4. Be 5 plus 1, which is 6, right? Go back to 1. Oh, yeah, this is kind of misleading. I invoke a different function. Okay, so that does look good. So far, so good, right? So we have the 0, we have the 1, 3, and 4. Okay, now we have the 2. It's best being. Wait, hold on, there's another. Okay, 3. Oh, let's do this. Consume this on the way back up. And it's. Oh, hold on, that doesn't matter. Oh, 6. Okay. 0, 3, 4. 2, 5, 6. Adding one too many there. Why am I adding one too many? Oh, maybe. Oh, yeah. Add ourselves on the way back. Hold on. T plus equals a sub u as a recursive stack on Wine's backup. Okay, I think that works. No, what am I doing? No, what the heck is this? It should be 3, but I'm seeing 4. Okay, 1 over and over again. How's T is 0? 0. At 0, I go from 0 to 1 to 3 to 4. The total is 6, so we consume that. Put the total back to 0. Then we go on to 2. Total is 5. Wait, when we go to 2, the total is. It was 6 when we go to 2. Okay, okay, hold on now. I'm not adding it until the end here now. Let's do this. This just doesn't seem to be helping. It seems to be overcomplicating things too, right? This is really discouraging. Okay, so the first one is okay. It's just zero by itself. Then we go 1, 3, 4. That's fine. We have 2. Now we're saying this one again. Which is, we go to 2. We can't separate 2. Okay, we can't separate. Okay, we can't separate 2 from 6 and 5. 6 and 5 need to be combined with 2, right? So, okay, I can't do this. 6 and 5 need to be combined with 2. So this one's not okay to handle. It's not a safe move. Okay, so T does plus equal A sub U here. With where are they? So that's not right. Here, shall I check here? Okay, all right. Oh, yeah, yeah. Yeah, okay. I have significant room for improvement, obviously. This looks good though, right? Okay. So I don't think it matters from the start. Make sure we have no regressions, right? So the first one should be 2, second one should be 3. That's good. Let's see what happens. Oh no. Expected 1. Oh, okay. The minimum of that minimum 1 at least. Okay, that's kind of a corner case, right? Oh no way. Oops, and the maximum, right? At least 1. Okay. Big money, no Emmys. Oh, it's 1 big expect 2. There's 2 edges. Or no, there's only 1 edge from 0 to 1. If I value 0, turn all in. So if there is no best, that means they all have to be zeros, right? Okay, that is a corner case for all n? No way, really? 1, 2, and 2, 0. I'm gonna write this down on a piece of paper. This is like taking freaking forever. Holy cow. All right. N equals 3. Edges is from 1 to 2, 2 to 0. To the values for 0 is 0. It's value 2, and 2 has value 2. K, or total, equals 4. So I'm not putting 1, but it's saying it's expecting 2. So, okay, I see. I do not need to check if t is 0. Okay, I think that'll do it. All right, big money, no Emmys. Looks good. Yay, all right, first try. Holy cow. Okay. Yeah. So note to self, if you're gonna do the as a recursive stack on lines, which I should, from leaf nodes back up in order to make sure there's a valid solution rather than cherry pick a node in the middle that we might not be able to successfully consume because the child subtrees, to leaves might be dependent upon it. So I made a non-safe move there. Oh, by the way, let's see what trend is. 923. It's 9:23. Yeah, I always lose a lot of time debugging. It's almost 20 minutes of debugging. The initial solution came in about 10 minutes. I have written about 10 minutes, came with a game plan. Then took 20 minutes to debug, right? Like painfully just going through each one step by step and failing forward. Seem to fail forward more efficiently. Yes. No, it doesn't. Yeah, sir. What's up, partner? Okay. Yeah. I'm finishing up. I'll be out in here in a second. Okay. All right. Yeah. It is family fun day, so hanging out with my kids not in here. Yeah, so arbitrary starting point is fine. Non-local best is updated as we go. Consume things as a recursive stack on lines. Okay, so this is easier than union find at least, though, right? It's pretty basic, actually. Daddy? Yes. I'll help you in a little bit, partner. Okay, I'm gonna finish up and I'll come hang out with you. Maybe mom will help you. Okay. Okay, okay. Okay. All right, note to self, keep it super simple. When I first came up with this, like that's way too complicated. And I thought, okay, yeah, union find I think would work too. You just do the union find as a recursive stack on lines, but it's overkill, right? You don't need to do union find. Just keep the track of the total as a recursive stack on lines and greatly consumed as we go. Right. So, and it would have been nice to have this epiphany, during the contest. But what's strange is I often come up with this when there's less pressure, right? So during the contest, I feel like I'm in a rush to come up with a solution quickly. But what I've found out is that speed is often irrelevant, especially if people fast is slow and slow is fast, and I'm part of people. So I have to constantly remind myself of that. Like if I want to go fast, I have to actually go slow first. So this was a painfully slow process, and this is what I'm going to keep on doing. And yeah, and we'll see what happens. I think I'm a work in progress, so it's fine. I don't need to pressure myself to be perfect. So in Python 3, it's just DFS, right? DFS consumption. And I'm pretty sure we can do BFS from leaf nodes too, right? Go up and then greatly consume it as you go. DFS seems fine to me though. Python 3, Rust, C++, Kotlin, JavaScript. And I think this is cool to have practice and to also see things in different perspectives, just doing these things in different languages. Okay, and then form DFS and accumulate the total T value of nodes as the recursive stack unwinds. To greedily consume totals evenly divisible by target T, by the input target T, and by target T. That's fine, right? Right? Create an adjacency list. Oops. Adjacent. Adjacency? Is that the thing? Adjacency? Yeah, okay. It looks weird. I don't know why. Adjacency list to associate nodes U, V. And E. And just number these things. 1, 2. It is, we increment the best answer by 1. Oops. And reset the total T to be propagated. Propagate it up, right? Propagate it up. That's the recursive stack unwinds. Starting at the leaf nodes. You sound good. Good. Looks good. Whatever. Okay. Create an adjacency list to associate nodes U, V for each edge and E. Perform DFS. I guess, yeah. Recursively go on DFS and accumulate the total T value of nodes as a recursive stack unwinds to greatly consume totals T evenly divisible by target T. That is, we increment the best answer by 1 and reset the total T to be propagated up as a recursive stack unwinds. Starting at belief nodes. Right. Node. Starting at node 0 is an arbitrary choice. It is safe to start at any node since a tree is a single connected component. Okay, that sounds good. Let's do these in the other languages, then I'll call it a day. All right, do C++. It's 9:32 in the AM, and it'd be really awesome if I get this done in a couple minutes so that you can eventually be a participant or a contestant, not just a participant in the contest, right? Super cool to see some other folks jamming on this. I want to see myself jamming too. Okay. Let's go. It is fun to go. Let's use our value semantics just for the hell of it. Let's see. Set of what's been seen as we go. We'll move it. Capture non-local best by reference into lambda. It will capture itself in its own lambda so it can recursively call itself. It's also going to capture best by reference, which is fine to do here in the LeetCode contest. In production code, we most certainly would not want to do this. Okay, take this as R by reference. What's been seen. Go. Scene to insert u subsecond. So scene to insert is a function that returns a pair. The first of the pair is an iterator to the value that's inserted or the value that already exists. The second of the pair is a Boolean, which indicates whether or not the value was inserted. So if it was inserted, it'd be true. So we're saying if it's false, which means it already exists, then we're gonna bail that early here. That way we don't run into a case where we recursively loop between nodes that have been previously seen over and over again. All right, we also need an adjacency list, which we'll use as the, say, adjacency list is the unordered map values between this adjacency list for each edge, list of edges, adjacency list of edge to the 0, insert edge to 1. Same thing, we'll do adjacency list of edge. So insert 0, with the bidirectional edges, it doesn't really matter. Let's do this actually. For each, you know, begin, you know, end, edge. Just grab that by that should be okay. You just stick it on the line. I don't know. It looks. Yeah, it looks okay. Right? Yeah, it's better like this. Or that's way better, right? I just stick the squigglies around it. We don't need a comma. It's fine. Yeah, that lines up better. Okay, so auto t is our total. Return t at the end here. for each edge B, which is adjacent to U. Right. E plus equals go B, move scene. If T is evenly divisible by T, oops, we set the total and increment the best. Okay, something like that, right? Oh, oh, come on. Uh-oh, that's not right. 5. Holy cow, this is way off. Best. What's going on here? What the heck? It's 9:38. So it took like 6 minutes to write, which is not too bad. Yeah, yeah, so I'm gonna be out here in a sec, okay, partner? Ooh, that's a good idea. Okay. All right. That sounds good, Sen. Okay, start at 0, return best. The heck? Why am I over counting? It has to do a scene. Come on. I think we have to pass. Let's simplify this, right? Let's just mark scene as something top level. We just capture it by reference. This will simplify anyhow. Oops. Oh, come on. Still recounting. Okay. But it does simplify the code. Okay. A bit easier to read, less verbose. All right, U is adjacent to V, V is adjacent to U, that's fine. It's not working. The heck? Why is it overcounting? Seriously, come on. I think. Oh, okay. I didn't add U, ace of U. Okay, duh. Okay, yeah, here we go. As the recursive stack on lines, right? We do want it. actually add something so it's not all zeros. Okay, I need to take a break, right? This is exhausting. Being interrupted by children and still trying to concentrate. Okay. Holy cow, this is not going that right. But yeah, that's a good sign to take a break. Let's see, that took about 9 minutes. All right, whatever. It is what it is. Right, 9 minutes for the implementation in C++, which is accepted, right? That's cool. And I'll come back to this. I'll practice it from try to get a little bit more speed and accuracy. Like create an adjacency list, associate nodes, you each edge. Yeah, right. Go perform TFS, accumulate this row of T value of nodes. Yeah, dang. I wish I would have wrote this during the contest. That would have been super cool. Okay, well, next time, to be continued.